So in the last lecture, we started proving the dissection principle. What we will do today is we'll quickly recap the notation for dissection principle and the statement of the theorem as well. And then we'll see how far we have gone in the proof and then start from there. So quickly recall that if you have a Markov chain that starts from state say 0 in this case, the first time it comes back to 0, it completes its first excursion. So here the first excursion is this part. And then the second time it comes back to 0, it finishes its second excursion and so on. And essentially dissection principle states that these excursions are valid under the appropriate probability. And in particular, first excursion would be independent of the second excursion. And as I said, it's kind of expected because the only part that is common is this part. And then future is sort of independent of the past. So therefore, one should expect it. And the common part is also deterministic because it's known to be at 0. So therefore, if the Markov chain does come back to its starting point over and over again, then we should expect that this excursion should be independent. That's precisely the statement of dissection principle. But quickly recall, we have taken a Markov chain on a state space S with transition matrix P that starts from a fixed state I. And then we define the 0th return time to be 0 because you're starting at I. So your 0th return time at I is 0. The first return time, 2I rather, is the first time after starting, the Markov chain comes back to I. Of course, it starts at I, but that doesn't count. You look at the first time, it comes back to I after that. So that's why you have to take the infimum over m bigger than or equal to 1. In particular, this means that this first return time is never 0. It's at least 1. Okay? But it's quite possible that this is not finite because the Markov chain starting from I may not return to I at all. So in that case, this would be defined to be infinite. If that is not the case, that is in the sense that suppose there is a finite time after which the Markov chain actually comes back to I, on that event, so on the event that the first return time is finite, we define the second return time I to I as the first time strictly after the first return time, the Markov chain comes back to I. Now continuing this way, on the event, by the way, so this means that the second return time is well defined only if the first return time is finite. Okay? It may not be finite though, it can still be infinite, second return time. But if it is well defined and finite, then condition on the event, both are finite, you can define the third return time and so on. So more generally, on the event that the first n return times are all well defined and finite, we can define the n plus 1th return time to I as the first time after the nth return time, the Markov chain comes back to I. Now in this picture, it's clear that the first return time is 2 and the second return time is 6. Now we define alpha k, we defined last time, to be the length of the kth excursion between visits to I. Okay? So in this case, the length of the first excursion therefore is 2 minus 0, which is 2. The length of the second excursion is 4 because you count after the first visit. For the second excursion, you count after the first return time. So after the first return time, it took 1, 2, 3, 4 steps to come back. So therefore, this length is 4 and so on. So the definition is therefore, alpha 1 is just the first return time. Alpha 2 is the difference between the second return time and the first return time. Of course, this is defined on the event when the first return time is finite. Because otherwise, second return time is not well defined and therefore alpha 2 is not well defined. And so on. You can define it this way. Now, the mth excursion would be the block that starts right after the mth return time. Sorry, mth excursion is the block that starts right after the m minus 1th return time, okay, and ends in the mth return time. Now, of course, this will be well defined provided the first m minus 1 return times are well defined and finite. Then only this is well defined. So on this event, therefore, this would be the mth excursion. So in this case, the first excursion is, first it goes to 1, then it goes to 0. So 1, comma 0. Second excursion in this case, after the first return time, we start. So it's 1, then 2, then 1, then 0. Okay. So we define the sequence xi k as follows. Xi1 is just length of the first excursion followed by the first excursion. On the event that the first return time is finite, Xi2 is just the second excursion followed by the, second length of the second excursion followed by the second excursion. And so on. You can go on. So when the first n return times are well defined and finite, on that event, okay, you define the nth random variable psi n plus 1, n plus 1th random variable psi n plus 1 as the length of the n plus 1th excursion followed by the n plus 1th excursion. Okay. What we will show not only that the excursions are IID, we will actually show excursions attached with their lengths. This entire vectors, this sequence of vectors are actually IID in a suitable sense. So in this example, therefore, we have two excursions. And I is 0, of course. And then the first random variable xi1 is 2, 1, 0. Why? Because 2 is the excursion length. First excursion length is 2. That's given by these 2. And then the excursion is 1, 0. So 2, 1, 0. Xi2 is the first excursion length, which is 1, 2, 3, 4. Followed by the excursion 1, 2, 1, 0.